This is a short video on the basic concept of specific heat of material, which is a part of Thermofluids lecture at UCL. And I've used this reference here in the book by Senjal and Bose titled Thermodynamics and Engineering Approach to Prepare the slides that we're going to be talking about. For any material, we have two different kinds of specific heat. Specific heat at constant volume and constant pressure. But before we get to the two different kinds, let's review what we mean by specific heat. Specific heat is energy required to raise the temperature of a unit mass of a substance by 1 degree centigrade. So if I look at my substance here and suppose it has mass of 1 kg, which is a unit mass, and I want to raise the temperature of this mass by 1 degrees, the amount of energy that I need to provide to this system or to this substance will be equal to the specific heat. Now, for a lot of materials, the energy required to raise the temperature by 1 degree depends on the kind of process that they are undergoing. And specifically, we can define two different kinds of specific heat depending on the type of material concerned. The first one is, of course, a CV, which is specific heat when the material is undergoing constant volume process, and the second one is constant pressure process-based specific heat. It's not always the case that we'll have two different values of specific heat, but often we do require these. So let's get into the details of what these two different specific heats are, how they are related to the other properties that we study in thermodynamics, and if there are situations where we can simplify these two specific heats into one single number and so on and so forth. So let's start with the constant volume one. So for constant volume specific heat, obviously we will be analyzing a constant volume system. So that's what I've got here. It's a rigid container which contains a certain amount of pure substance of unit mass, and I'm putting in some amount of heat in order to raise the temperature of this mass. So how should I go about analyzing this system? Well, I start with my basic energy balance. This is a closed system, no exchange of mass, so I've got energy input minus energy output should be equal to the change in energy of my system. If I want to analyze small energy changes, I can take derivative both sides. So this becomes del E in minus del E out. Why del here? Because these two are path functions, right? Energy transfer across the system happens in form of heat and work, both of which are path functions. So these two input and output energies are path functions, and that's why I write del here. And then change of energy, small change of energy of the system, which is the property of the system, so I don't need del for that, it's a point function, so I write that as dE system. So the system that we are analyzing here is not very bulky. It has 1 kilogram of mass, and it's not, there is not substantial change in the height in the system if I'm analyzing a fairly small system. What I'm trying to get to is I can safely disregard the change in kinetic and potential energy for the system. And if I do that, then the change in energy of the system becomes nothing but equal to the change in internal energy of the system. So I get my energy balance equation reduced in this form here. And I've done one more thing here. As you will notice, I have replaced the delta E in by the delta Q in, or the heat that I'm putting into my system, right? Now, this is a rigid container, right? So it's not expanding or anything, and I don't have any other form of energy leaving the system. So I can safely disregard the energy output. So what I get is del Q in, which is the differential energy input, is equal to the du, the change in internal energy of the system. Now, by definition, the heat that I'm providing will change the temperature, right? So I can write this heat input as CV times dt. Why CV, or constant or specific heat at constant volume? Because we are analyzing a system at constant volume. So that's exactly what I'll do next. So this is del Q in is equal to CV dt. This is by definition true. That's the definition of specific heat. The heat that I put in is equal to specific heat times the change in temperature, right? Which is what dt is. And because we are analyzing a constant volume process, I write that as CV times dt. So now that I've got del Q in as CV dt, I can substitute here. So I get du equals CV dt because dq in is CV dt, right? And I call that as equation 1. And if you notice, this is a property relationship. It relates internal energy, which is a property of the system, temperature T, another property, and CV, which is also a property of the system. Now, if I manipulate this equation a little bit, I can get CV as du dt, but I have replaced this du dt as partial derivatives because we did this derivation assuming that volume was constant. If the volume is not constant, the derivative would look very different, and that's what is represented by this partial derivative, which is written as this curly t here. Okay. So partial derivative of u with respect to time at constant volume is what CV is. This, if you will, is thermodynamic definition of specific heat. Okay, but life is not always this complicated. There are situations where CV can be assumed to be a constant and it does not vary with temperature a lot. And if that's the case, then I can go back to this equation here and I can integrate this equation between, let's say, a state 1 and state 2. If my system were to undergo a change or a process from a state 1 to 2, and if in that process my CV happens not to vary too much, or if it remains constant, this can happen, let's say for instance, in a situation where the temperature change is not much, then I can write U2 minus U1 by integration is equal to CV times T2 minus T1. This is following directly from this equation 1 by integration, okay, in a situation where CV is constant. Okay. If that is not the case, you have to stay, unfortunately, with this basic relationship. But for a small change, we can always assume CV to be a constant. So this du equals CV dt is valid regardless of whether CV is a function of temperature or not. This is a property relationship. That's the beauty of property relationship. They are valid regardless of any process, etc., that your system may be undergoing. Okay, so that was specific heat at constant volume. Let's do the same thing for CP, the constant pressure specific heat. So in this case now, I have to start with a system which is undergoing a constant pressure process. So we go back to our favorite example of a cylinder with a piston on top, and this piston is free to move in a frictionless manner in such a way that the pressure is maintained to be constant, right? So again, I'm putting it Q in as heat, and I want to analyze this system in order to get to the definition of CP in this case. So like before, I start with my energy balance, which is E in minus E out is equal to delta E of the system, and I again take derivative to get del E in minus del E out equals del dE of the system. So change in energy of the system. Now in this case, again, what about my energy input? Well, energy input is given, that's del Q in, so I substitute that here, minus del E out. Now in this case, energy output is not zero, because if this system moves upward freely because of heat being put in here, this is a constant pressure process, so the piston is free to move, and if the piston moves up, it is going to do some work on its surrounding by expansion of this boundary here, right? And we call that as boundary work, and boundary work is nothing but P times dV. So I substitute this del E out as P dV. So I get del Q in minus P dV equals du. Again, in this case, I have disregarded the change in potential and kinetic energy, which is a reasonable thing to do for a small system that we are trying to analyze, right? So we get dq in minus pdv equal du. So the basic difference is that in this case, because it's a constant pressure process, we have some amount of boundary work associated with it too. And that's why we need different specific heat for this case. So be that as it may, by definition, dq in is equal to the specific heat times the change in temperature. So I go back to the definition of specific heat and I write dq in equals specific heat times gt. And of course, because we are analyzing a constant pressure process, I write the specific heat in this case as Cp dt. Okay, so the only thing that is remaining to do is to substitute del q in equals Cp dt, which is here. And I can take PDV to the other side, so this side will become du plus PDV, and that's what I've written here, du plus PDV, because I move PDV to this other side, so du plus PDV is equal to Cp dt, because that's what del Q in is by this expression here. So again, you are getting a property relationship. Of course, this looks a little bit different. So it's not du equals Cv dt, but du plus PDV equals Cp dt, right? So this is again a property relationship that is valid regardless of the process concerned. That's the beauty of property relationships. So let's carry on with it. So this is where we have reached so far. Du plus PDV equals Cp dt. And let's see if we can further manipulate this. So now we know that enthalpy is defined as H equals U plus P times specific volume. This is by definition true, where each of these are written as specific quantities, right? So per unit mass basis. So if I start with this equation here, I can differentiate both sides again. So on the left hand side I get dH, and then derivative of U is du, and then I've got a product of two quantities here, so I write that as P times dV, so derivative of the first where or the second where first is held constant, and then the second is held constant and derivative of the second. This is what chain rule is, right? So I get dH equal du plus pdV plus vdp. Now if you go back to the system that you are analyzing, you're analyzing a constant pressure process, right? So by definition, your dP has to be equal to 0. There is no change in process because it's a constant pressure process. So I can set that equal to 0. What does that give me? Well, what do you see here on the right hand side? du plus vdv, right? And that's what I've got on the left hand side here. So I can replace this du plus vdv with dH, one single enthalpy, right? So what do I get as a result? dH, because that's what du plus pdv is from here, equals Cp dt. It's a much more simplified form of property relationship, which relates change in enthalpy with Cp times dt. And again, like before, I can manipulate this and write Cp as partial derivative of H with respect to time at constant pressure. And again, this is because we have done the derivation with the limitation of pressure being constant. And like before, if Cp is constant and it doesn't vary with temperature, then we can integrate this equation 2 in this case to get H2 minus H1 between the two different states of 1 to 2 equals Cp times T2 minus T1. This is not always true because Cp is not always constant, but if the change in temperature is not much, then this holds fine. So to summarize the whole thing, we have identified two different kinds of specific heats, and we did the derivation to find out Cv equals partial derivative of U with respect to temperature at constant volume, and Cp equals partial derivative of H, which is enthalpy with respect to temperature at constant pressure. And you will note that these are general definition, first of all. Okay, these are valid for any substance. Okay, nothing about ideal gas or anything like that. These are always true. These are thermodynamic definitions. And we also found out from these relations that Cv is related to internal energy, U, and Cp is directly related to enthalpy. So this makes, this gives us another reason for introducing enthalpy as a property, if you will. What is the unit of specific heat? For both of these, the unit is going to be kilojoule per kg Kelvin, okay, in the SI unit that we are considering. Now, a while back, there was a question in the class about whether Cp is greater than Cv. In fact, that's always true. Cp is always greater than Cv if they are different from one another. And the reason for that is because when we derived Cp, you'll remember we derived it for a constant pressure process. So for a constant pressure process, the system can expand and it ends up doing some amount of work on the surrounding. So the energy that you put in not only raises the temperature of your system, but it also is part of it is used to provide work to the surrounding, right? So the energy required by you in a constant pressure process is always higher because you need to do some work on the surrounding as well. And that's why Cp is always greater than Cv. Okay? So let's now start by analyzing how Cp and Cv change as we start to analyze different systems. It turns out life is not always as complicated. We can make some simplifications. So let's start with ideal gases now. For ideal gases, there is a very unique characteristic that Cp and Cv have, and that is that they are only functions of temperature. So in general, a property should depend, we know, from our first few lecture, a property should depend on two different independent properties, right? But that's not always true. For ideal gases, which are very specific case, internal energy and enthalpy are functions only of temperature. Now, true that ideal gases don't exist, but in a lot of situations, we can approximate real gases as ideal gases. So, for instance, if we take air at reasonable pressures, right, around 1 atmospheric pressure and around room temperature, we can approximate it as an ideal gas. And as a matter of fact, to prove the fact that internal energy and enthalpy are only functions of temperature, James Joule did a very nice experiment, which is what I've shown here. So what he had was two different, let's say, spherical containers, and he put air at a reasonably high pressure. This is not, we're not talking about hundreds of atmosphere in terms of pressure here. It's just that he had relatively high pressure here, and he evacuated this chamber on the right hand side, this little chamber, white chamber on the right hand side, and he put a valve in between. Okay, so in between, in the beginning, he had air on this side at slightly higher pressure than on this side, which was evacuated. And the next thing he did was he put the whole thing in a water bath, okay, which he insulated from outside, and he put a thermometer in here. So basically, the idea was to show that if you open this valve here, what do you have? You have air from here at high pressure. It's going to go and it's going to make its way to this evacuated chamber, right? Because the pressure here is higher than pressure here. So essentially, this air here will expand. So obviously, this air is undergoing a change in its property, which is volume, right? And so, because it's undergoing a change in its volume, we may expect that in the process, this air will undergo a change in temperature, okay, a change in its internal energy, right? But what James Joule saw was that this thermometer here did not record any change in temperature. So that means whatever happened here did not cause the temperature of water in the surrounding here to change. That means there was no heat exchange between this gas and water outside, even though he was using metallic spheres as containers here. So that means by volumic change, there is no change in heat transfer, or there is no heat transfer across the boundary. Now if you think about it, what is the system we are analyzing? We are analyzing air at moderate pressures, as I told you. So this is a good approximation of internal energy. Now if you consider this whole system, okay, this whole container as your system, there is no heat going in or energy going or work going in or heat going out or energy going out. So this is an isolated system, okay, and because of this expansion there is no change in temperature, and we have not put any energy from outside to change the temperature. Essentially we are analyzing a system where the temperature is not undergoing any change. Okay, so if the temperature is not changing, we are not recording anything on the thermometer, obviously, right? And if the thermometer is not recording anything, we can say that, okay, because we did not change the temperature of the system, the internal energy of the system is not changing at all. Okay, so by doing this simple experiment, he was able to prove that the internal energy is only a function of temperature of the system. Because see, you have not changed the overall energy of the system. He took pains to isolate the whole thing. He took pains to put insulation here. So he was making sure that he was not putting in any energy into the system. So regardless of what you change here, he expected no temperature change. And that's what he found out. But if this was a real gas, if there was a sufficient amount of expansion here, the real gas will undergo a change in temperature. But because he was considering moderate pressures, this gas was behaving as an ideal gas. So because he didn't put any energy from outside and there was no change in internal energy of the system, because there was no energy being put in, there was no temperature change recorded here. So he used that to conclude that the internal energy of an ideal gas is going to be a function of temperature only. Okay? And because for an ideal gas, or for any gas for that matter, or any fluid for that matter, you can write by definition H is equal to U plus PV. Now, if the gas is ideal, you can write PV equals RT, where P is pressure, V is specific volume, so volume per unit mass, is equal to the gas constant of the gas. This is not universal constant, but this is universal constant Ru divided by molecular weight. Keep that in mind, according to the notation we use. And this is temperature in Kelvin. So I can substitute PV here in terms of RT. So for ideal gas, what we are getting is H is equal to U plus RT. So what do you get here? This R is a constant, and we just said that U is a function of temperature only because we are analyzing ideal gas now. We get H also a function of temperature because this R is a constant. So we're getting both U and H as a function of temperature. And we can take derivative again by using the relationships that we derived, which are valid for any substance, which was du equals Cv. Now for ideal gases, Cv is only a function of temperature because du is a function of temperature only. And similarly, we can show that dH is only a function of temperature because by definition, dH is Cp times dt. And we just said that H is a function of temperature, dt is temperature. So Cp is a function of temperature only. What this is telling us is that for ideal gases, Cp and Cv are only functions of temperature, right? Not always. So this is first important relationship. If we start with this equation here, where du is Cv function of temperature only for ideal gases times dt, we can integrate it again, right? And now, even for ideal gas, if Cv is a function of temperature, I have to write from 1 to 2, state 1 to 2, Cv times dt, and I can't simply take it out of the integration. You see, that's why I was emphasizing that you can take out the Cv out of this integration only if Cv were to be constant. And that will happen if your state 1 and 2 do not have much by way of temperature changes. So if the temperature change is small, so that your CV and CP are relatively constant, then you can take CV out. And you can do the same thing, of course, with the CP relationship, and the second one here. So you can write H2 minus H1 as integration 1 to 2 CP dt. Right? So that's how your internal energy changes are, internal energy and enthalpy changes are related to CV and CP in the general case for ideal gases. What else can we do? Well, um, we are staying on with ideal gases again. So we have H equal U plus RT. We derive that. We can differentiate this guy. We can get dH equals du. Derivative of U is du. Times R is a constant times dt, right? And again, by definition, we have dH equals Cp dt and du equals Cv dt. So I can substitute for dH as Cp dt. So this becomes Cp dt on the left hand side. Du is Cv dt, so I can substitute that here, plus rdt. Okay, so I'm getting a relationship between Cp and Cv essentially, because I can now cancel out dt, dt, and dt here to give me Cp equals Cv plus R, where this R is again for specific to a gas, because this is universal gas constant divided by m. We can multiply the whole thing with molecular weight as well, and get this expression in terms of moles. So if Cp bar is your specific heat for unit mole, when you're considering this expression in terms of molar basis, you can write that as Cp bar equals Cv bar plus Ru. Now this is a universal gas constant. And if we take the ratio of this Cp and Cv, and that's what we define as specific heat ratio, K, that's equal to Cp by Cv. The good thing is that even for a lot of real gases, this Cp Cv ratio does not vary much. So for monatomic gases like helium, argon, and other ideal gases, experimentally this has been measured to remain constant at around 1.667. For diatomic gases, it's about 1.4. For air, it's around 1.4 actually, and this is a value that is used quite commonly. Now for air, we will, for some of our problems that we will be solving, at around 300 Kelvin, which is room temperature, Cv is about 0.718 kilojoule per kg Kelvin. R for air, which is this gas constant for air itself, is equal to 0.287 kilojoule per kg. So if you put both of these Cv and R in here, you will calculate Cp as equal to 1.005 kilojoule per kg. And per molar basis, you can convert it by using molecular weight of air, right? So these expressions here we will be making use of, because we'll do a lot of calculations using air, and in a lot of situations we'll assume Cp and Cv to remain constant at these values. Although we do know that Cp and Cv vary quite a lot with temperature, but if the temperature changes are not much, so let's say 10, 20, 30 degrees centigrade or in that ballpark, then we can use Cp and Cv to be constant at around these values here. Okay, so for real gases, life is not that simple, right? So for real gases, we can't simply write U and H as to be simply related to Cp and Cv. But if your temperature change is not much, then for real gases like air, we have tables where these are called ideal gas table for gases, where we list U and H directly as a function of temperature, right? We could very well, put Cp and Cv as a function of temperature as well, and some tables also do that, because oftentimes it becomes convenient to use Cp, Cv. But in a lot of cases we tabulate U and H directly. If you don't have U and H directly known for real gases, you can go back to what we derived earlier, which was U2 minus U1 equals CV times T2 minus T1, of course with the assumption that CV is not changing much as a function of temperature, and the same thing for the change in enthalpy here. Okay, so these are approximations that we quite often make for real gases. Okay, so that covers gases, right? So if we backtrack for a second, how did we approach this? We introduced the fact that we have two different specific heats for any substance, Cp and Cv. Then we said for ideal gases, Cp and Cv are related to each other because of the fact that their internal energy and enthalpy are functions of only temperature. And then we are now going to gradually complicate things. So now we analyzed real gases, and we said that we have tables where we can look up U and H directly as a function of temperature. And if in specific case our Cp and Cv are not varying much, and that happens if the temperature change is not much for a process, we can write the change in internal energy as Cv times T2 minus T1 and change in enthalpy as Cp times T2 minus T1. Okay, and we will be solving a lot of examples which will make use of this, so this will become clear to you as you start to solve problems and so on. Yeah. So what else can we have? Well, what about liquids and solids? In a way, we could have started with this, but I chose to keep it at the end because solids and liquids are fairly simple to analyze so far as their specific heats are concerned. And that's because most solids and liquids that we know for reasonable thermodynamic processes can be assumed as incompressible substances. That means if we increase pressure on them, their volume does not change much. And for incompressible substances, Cp and Cv are equal to one another. Okay, so these are not gases. Okay, so it's not that Cp is equal to Cv plus R for ideal gas and so on and so forth. So for incompressible substances, Cp and Cv are equal to one another. That's why in high school, when we learn about specific heat, we don't bother talking about two different specific heats because we have not studied thermodynamics until that point, right? So for liquids and gases, to a very good approximation, we can write there is only one specific heat, and that's equal to Cv and Cp because they are both one and the same for incompressible substances, right? Which are solids and lots of liquids. And also, this specific heat, although it changes with temperature, but again, for liquids and gases as well, if the change in temperature is not too significant, oftentimes we make the approximation that Cp and Cv both, which are equal to one another now, are constants. Okay? So, what do we do for liquids and solids? Well, we start with the basic definition, the property relation. Remember, I said the property relations are valid for any material and for any process that they may be undergoing. So du is always equal to Cv times dt. Now, if you are analyzing solids and liquids, I just said that Cp and Cv are equal to each other, and let's say that Cp, Cv, I just call them as C, just specific heat. And of course, for solids and liquids as well, C is a function of temperature only. So I can write du as equal to C as a function of temperature times dt. And if I integrate this for solids and liquids, I get between two states of 1 to 2, I get u2 minus u1, which is delta u, as 1 to 2 integrated Ct times dt. And if the temperature change is not much, I can approximate my specific heat here to an average value, right? Oftentimes, for convenience of analysis, we take this as room temperature. If you want to be slightly more accurate, you can take this as the specific heat C at the average temperature between 1 and 2, or any other form of average that is reasonable enough. The point is, if for whatever constant you settle at, if this becomes a constant, it can be taken out of the integration. Integration of dt from 1 to 2 is nothing but T2 minus T1. So I can write delta U approximately equal to the average value of specific heat times T2 minus T1. Okay, this is used very often, and this approximate sign, the change in energy of the system, is equal to specific heat times temperature change. Remember, this is something that you have been using for quite a while now, and now this gives you a framework for how these relationships come about. All right. So, as I said in the beginning, I've used the Senjal Bols's book to prepare these slides, and you'll find the material for this in chapter 4 of the book. I had assigned the chapter 4 as a reading material, so you can review that one more time in order to, let's say, better appreciate these concepts, and we can discuss these more in our classroom lecture. Thanks.